All right, let's talk about something that sounds super complex but is actually critical for anyone working with industrial machinery: functional safety. We're going to peel back the layers and demystify this whole topic because it all comes down to one really important idea: making sure that when things inevitably fail, people don't get hurt. Now, this might sound a little backward, right? But this is the absolute bedrock of functional safety. You have to start with this core philosophy. We just assume that every single component, every switch, every wire, every processor is eventually going to break. And our entire job is to build a system that's ready for that moment. So let's dive right in. What is the real difference between a machine that just works and one that is genuinely, reliably safe? That gap, that's where functional safety comes into play. Okay, picture this. You've got a big hydraulic press and a light curtain. Simple enough. You stick your hand through the light beam and bam, the press stops. It works perfectly. The safety function does its job, at least for now. And that's the million-dollar question, isn't it? Will it always stop? What happens if the one relay controlling that press gets stuck in the on position? Or what if the sensor itself fails at the exact moment your hand is in the danger zone? That's the stuff that keeps safety engineers up at night. See, in that light curtain example, if you're relying on a single chain of components, you're vulnerable. If just one of those links breaks, the whole safety function is gone. And that's exactly the problem that standards like ISO 1384-1 were created to solve. They move us away from just crossing our fingers and hoping it works, to being able to mathematically prove it will. To really solve this, we can't just talk about safety in fuzzy terms. We have to get specific. We have to turn it into a number, an actual engineering target that our system has to be able to hit. No excuses. And this isn't about guesswork. It's a very structured process. First, you analyze the machine. You identify every possible thing that could go wrong. Then you evaluate just how bad each of those risks is. And only then can you start designing the right protections to bring that risk down to an acceptable level. So how do we actually estimate that risk? Well, we look at three key things. S is for severity. Are we talking about a minor cut or a life-changing injury? F is for frequency. How often is someone actually near this hazard? And P is for possibility. If something does go wrong, is it even possible for the person to jump out of the way in time? You take those three factors, you put them together, and they give you a very specific target. It's not a suggestion, it's a hard requirement. We call it the required performance level, or PLR for short. Our safety system has to be engineered to meet or beat that level. So, for example, after going through that whole process, our risk assessment might spit out a target of performance level D. Okay, that's our goal. Now the real fun begins. How do we actually build a system that can hit that target every single time? All right, so we've got our target. Now, what tools do we have to actually build a system that meets it? Let's get into the engineer's toolkit and look at the core building blocks from the ISO 13849-1 standard. The most powerful tool we have is redundancy. Think about it like this. A single-channel system is like an airplane with only one pilot. If that pilot has a problem, you've got a huge problem. A dual-channel or redundant system is like having two pilots in the cockpit. They're both flying the plane, and they're constantly cross-checking each other's work. If one makes a mistake, the other one is right there to take over. The plane stays safe. Now, hitting our performance level target isn't about just one thing. It's more like a recipe with 4 key ingredients. You've got the category, which is the basic architecture we just talked about. Then you add the reliability of your components, the MTFD. Then you factor in how well the system can find its own faults, which is its DC. And finally, you have to account for CCF, which is all about making sure one single event can't cause both of your redundant channels to fail at the same time. You need all 4 of these to prove you've hit your target. So let's break those down. MTTFD sounds complicated, but it's really all about using high-quality parts. It's a statistic that tells you, on average, how long a component should work before it fails in a dangerous way. The higher the number, the better. We're talking about using proven, reliable components and having the data from the manufacturer to back it up. And this one is my favorite, diagnostic coverage. This is the system's ability to check itself for problems. Think of it like your car's check engine light. A good safety system is constantly running these little internal tests, looking for hidden faults. A high DC means the system is really good at finding a problem and shutting down safely before you ever need it in an emergency. Okay, that's enough theory for now. let's get practical. How does all this stuff actually look when it's built with real hardware on the factory floor? On the surface, a standard PLC and a safety PLC might look similar, but inside, they are worlds apart. A standard PLC is designed to keep the machine running no matter what. A safety PLC, like a guard Logix, has two processors inside, a primary and a safety partner. They're running the exact same logic in lockstep, and they are constantly comparing their results. The instant there's any disagreement, even a tiny one, the system defaults to a safe, de-energized state. Now, back in the day, safety systems needed their own separate, complicated, and expensive wiring. It was a total headache. But now, we have protocols like CIP safety. This is just a brilliant piece of engineering that lets our safety devices talk to each other over the same standard Ethernet network as everything else. It just adds this clever safety layer on top, with things like timestamps and unique IDs to make absolutely sure no safety messages ever get lost or corrupted. So you've spent all this time building and validating your safety logic. How do you make sure nobody messes with it? That's where the safety signature comes in. The best way to think of it is like a digital tamper-evident seal on a medicine bottle. The controller creates this unique code from your safety logic. If anyone, intentionally or not, makes a single change to that logic, the signature breaks and the whole system faults to a safe state. It's a fantastic failsafe. And all of this technology leads us to a really cool evolution in how we think about safety. It's not just about slamming on the brakes anymore. Modern safety is about being smart and actually helping improve productivity. This quote really captures a massive shift in mindset. Instead of treating a safety stop like some kind of disaster, we now treat it as a normal, totally expected part of the machine's operation. Someone breaking a light curtain is an emergency. It's just business as usual. And the new goal is to design the machine to recover from that event as fast as humanly possible. And this is where these advanced functions become game changers. Something like Safe Torque Off, or STO, can kill the motor's ability to spin without powering down the whole drive, which means you can restart way faster. But the really amazing one is Safely Limited Speed, or SLS. This lets an operator actually go inside a machine to clear a jam or do a setup task while the machine is still running at a guaranteed, safely monitored slow speed. That can completely eliminate the downtime of a full stop and restart cycle. So, I'll leave you with this question to think about for your own operations. Is your safety system just an obstacle? Something that gets in the way and costs you time and money? Or have you turned it into an intelligent asset that not only protects your people, but actually makes your whole operation run smoother and more efficiently? Because the technology to do that is here, right now.